Good afternoon, everybody, and welcome to today's OCCA webinar, which will be presented by one of our corporate sponsors, X-Rite. So my name is Nikki Cosgrove. I'm the Vice President of OCCA, and first I'd just like to take a couple of minutes to tell you about OCCA and who we are and what we do. So we're a professional association and a learned body, and our membership comprises of individuals from around the world working or studying in the coatings or allied sectors. Currently, our membership exceeds 800 members, headquartered here in the UK, with members living and working in the UK, Europe, Central and Southern Asia, South Africa and beyond. OCCA also has sister associations in South Africa, Australia and New Zealand. We exist to foster and develop education and training and to promote the links between academia and industry. We currently offer 2 bursary schemes designed to help students in full or part-time education to gain qualifications in their chosen subjects allied to our industry. OCCA's main activities are centred around webinars such as these, regional seminars and other networking and social events, both at a regional and a national level. I should point out that OCCA is a registered charity and is run in the main by a group of volunteers. The most important date in the OCCA calendar is Surfex. This is the only UK exclusive coatings exhibition and is held every other year. And as 2020 had to be cancelled due to the pandemic, we're very much looking forward to seeing our members, colleagues and friends next week. If you haven't already done so, there is still time to register on the Surfex website. Why not come along to the OCCA stand and say hello to the team? So as well as the exhibition itself, there are 4 conference streams at Surfex, all running in parallel over both days, meaning that you can hop in between conference streams and build your own conference programme. There's no limit to the number of conference sessions that you can attend, and attendance is free. There is plenty of time factored into the morning, afternoon and lunch breaks for you to visit the exhibition, so careful planning in advance is essential so that you can see all the exhibitors and go to all the conference sessions that are important to you. All of the timings and information can be found on the Surfex website. On the evening of the 7th of June, we will be holding our OCCA Surfex charity dinner, which is always good fun and a chance to network socially. In addition to the evening's entertainment, we will also be holding a charity raffle in aid of our chosen charities, which are KidScan, which is a children's cancer research, Alzheimer's Society, the British Heart Foundation, and Breast Unit, which is part of the Princess Alexandria Hospital charity. One of the benefits for our members is our award-winning Surface Coatings International Journal, published by a team of volunteers and overseen by our technical editor, Dr. Richard Kennedy. We produce 6 issues a year, packed full of industry news, technical articles, product showcases, technical perspectives, association news, and calendars of coatings industry events. Each member receives all 6 issues either in printed or digital format, and in addition, companies are eligible to purchase annual subscriptions to this publication. Please see our website for more details. OCCA are extremely grateful to our 22 corporate sponsors who not only support the association financially, but who also contribute greatly to our webinar programme, our SCI Journal and the Industry Insight Days and other mentoring sessions that we set up with our partner universities. If you or your company would like more information on how to get involved with this scheme, please contact Anne-Marie Etherington on the admin email address. Currently, we're working with 6 university partners who've teamed up with us as educational partners. We are also speaking to a similar number of new universities who we hope to be bringing on board in the near future. This enables OCCA to engage with our partners and forge closer links between academia and industry, especially with the help of our corporate sponsors and other members who get involved with industry insight days, guest lecturing and mentoring schemes. We also hope to push our newly launched OCCA and Surfex bursary schemes with the help of those partners. On the flip side, members can benefit by offering short or medium-term placements for students and accessing many of the grants-funded initiatives and knowledge transfer partnership schemes that the universities have to offer. So now I would like to introduce our guest speaker today, Matthew Adby from X-Rite, who's going to deliver a presentation on advances in hyperspectral colour measurement, improvements in paint match performance and sample acquisition. So just a brief bio on Matthew. Matthew joined X-Rite in 1998 with progression through application support, sales account management and product management, and is now responsible for product portfolio management within the markets of consumer products and materials, retail, appearance and automotive products. X-Rite manufacture, market and support innovative technology-based solutions for global markets, where colour and appearance matter, from inspiration through production for the purpose of creating economic value while considering the environmental and social responsibilities. Matthew's current role includes managing a team of product managers that help define market roadmaps, develop business models and strategic partnerships, and work closely with customers to validate product concepts. Prior to joining X-Rite, Matthew worked for 11 years in the paint industry, operating in architectural, protective and automotive sectors, and holding research and development, quality control and production development roles. Before I hand over to Matthew, please can I ask that if anybody has any questions regarding the seminar, please can you enter them in the question and answer box, and we'll come to those at the end of the presentation. So Matthew, over to you.
Thanks very much, Nikki. And yeah, first of all, thank you for Oil and Colour Chemists Association for inviting me to talk. It's a real privilege. And also, it's been such a long time as well. I've actually been an associate with OCCA, I think, for over 35 years, going well back into the days when I used to work for Sigma PPG. And today I'd like to actually start to talk to you about some of the things that have changed over those years of how we're actually measuring our paint colours. And we can see that things today are quite different. But before we actually go into those new technologies, I wanted first of all just to give a short reminder about what is colour, how we see colour. As we can see on the screen now, this first colour sensing process, I always like to describe how we see the colour. First of all, for there to be a colour, there has to be a light source. Without a light source, there's obviously no colour. We have to have an object that's going to absorb or reflect a certain amount of light. And lastly, your eye, the observer, which we're going to use the cones within your eye to be able to detect the colour. One of the examples I also like to talk about is people say, well, what is the colour of the inside of my refrigerator? Well, when the door is closed, it's obviously black because there is no light, the light is not on. As we then start to move towards, well, how do we communicate colour? To communicate colour, we need to first of all understand what that light source is, because as I said, the different types of light source. So if we look at a color under a fluorescent light, if we look at under a tungsten light, if we look at under a red light, that will affect how the light is absorbed or reflected back onto that object. And finally, we need to understand how that observer is observing the object. Because if you observe things either at close distance, further away, etc., that will actually change your observation. When we add each of these things together, this enables us to be able to have color communication. Typically, most people think of that as LAB, but we first of all need to, I think, go one step deeper to understand how those colors are made up. Well, to understand how it's made up, I think the best thing is for us to understand actually how a spectrophotometer works. As we said, light shines onto an object and a proportion is absorbed and a proportion is reflected back. Typically, a spectrophotometer has an internal light source. It shines that light onto the object. And the examples here you can see where we have the blue, the green, the red. These are made up in their fingerprint, their spectral curve, which indicate the light combination to be able to create those colors. Next, there are different types or different geometries of spectrophotometers. There are three key types. The first one is what we call 045, or sometimes called 45-0, because we can actually reverse these. These are typically used in the printing industry. They are also sometimes used in the paint industry, but these are, we might class it as being the most simple type of optics or illumination. The basic principle is either we have a receiver or a lamp at the 45 and the 0. In this example here, the light shines down at the 45 degree, and at the 0 angle, we have a receiver. Therefore, it's important to understand that only a proportion of the light which is actually scattered and not the specular light which is reflected, is actually seen by the observer. This is important to understand because if we have a glossy sample compared to a matte sample, we will see a difference, because a glossy sample will actually have the light which is reflected back at the equal and opposite angle and will be lost, and therefore a glossy sample would look darker in shade than it would if we had a matte sample that equally scatters light in all directions. As we move then towards the diffuse 8 sphere, this is the typical device that's been used in the paint industry, in textiles, and this is where we are also interested to understand the effect of the surface texture or the gloss of the sample. In the most simple way to describe this, if we imagine illuminating, and this object, this sphere, is like a table tennis ball, a ping pong ball, that light is going to be diffuse and is going to illuminate onto your sample. And when we have it in what we call the specular included, this means that all the light that shines onto that object is going to be collected and received back. This is important because that means that whether your sample is matte or whether it's gloss, it should read the same. These devices, though, have what they call a specular excluded port. This excluded port can be a physical port that opens, that allows that specular light to shine back out, and therefore it acts in a similar way to the 045, meaning that a glossy sample in a specular excluded will actually look darker in shade than a matte sample. The final piece for us to look at is the multi-angle device. These are typically used in the automotive paint market, where we have the effects, metallic, silver paints, etc. And these are needed because with a metallic sample, the color of the observation is dependent on where the light is shining from and also from where you're observing it. And this is where we talk about having the face, the flash, and also the flop angle to understand how the light is falling onto it. Now, each of these, as I said, actually perform measurements in a slightly different way, and typically you have slightly different data. But what I'm going to talk today about is also some of the challenges, because these all measure in what I call a spot measurement. That means that typically they measure in an area, perhaps like an 8, 10, or 12, or sometimes in a 24mm area, but this is going to be a solid color, a solid area of measurement. That can give us some challenges, because as we look towards these traditional spectrophotometers, they are very, very good if we are measuring solid areas of color. So you see here, for example, this color chip, this fan deck, or perhaps if it's a solid paint sample, these are very good, no problem at all. Likewise, if we have a standard piece of textile, so for example, like my shirt, again, no problem measuring that because it's a homogeneous color, it's a solid color, no problems. What we do find, though, is difficulties when we start to look at more lifelike everyday samples, when we have challenges such as measuring pieces of carpet which have a heavy texture, measuring very small samples because perhaps they don't fit inside that measurement area. Likewise, when we have patterned and multicolored shades, how do we actually extract the color from either a small area or an area which might have multiple shades? We have challenges also when we think about shaped objects, how we can actually get to that shape. And also we shouldn't forget things like with the paint industry, one of the challenges here is wet paint or inconsistent paint. We need to be able to understand how each of these are going to affect your visual result. So let's go one step deeper. Let's look at the spot measurement versus what we call the hyperspectral image. Well, if we take the example here, this piece of fabric, we can see it in the camera, the reticule, and we can see that we have two distinct color areas. We have this sort of pink color and we have this like close to black color. If we measure this in a traditional method, that complete measurement area would be averaged, and therefore the result is a combination of the pink and the black, and therefore you get this darker shade. What we want to understand is, how do we actually get the true color? How do I measure the pink? How do I measure the black? Well, if we use a pixel-based solution or a hyperspectral imaging, we can achieve the reflectance measurements for each pixel which is within this image, and therefore achieve the correct view to be able to see that bright pink and the black. Looking then how that's achieved in a device, this is the X-Rite meta view, or we also call it VS3100 or VS3200, depending on the model. This has two really interesting characteristics with it. The first is that it uses a camera. So traditionally, spectrophotometers use a sensor, and they have a sensor to measure, as you remember, how much light is coming back at each of those wavelengths. This actually uses a very special type of camera, and it will then view the colors through a filter wheel. 31 points in this filter, which gives our 400 to 700 nanometers, the same as we have with our spectrophotometer. The second point that's very interesting with this is a non-contact device. It uses these three illuminators to illuminate from the three directions, and this is at that 45-0 geometry, and allows us to make a measurement at close distance to the sample, but not in contact with it. It's interesting when we start to look at the images and what we can do, because what we have to understand is different type of objects have different types of challenges. So looking at this first problem with this piece of like masonry facade textured sample, you can see in here that it has cracks, lines, bumps, troughs, holes, all sorts of pieces which are causing problems. If we measure this with again a spot measurement device, it will include all these components and will average it together. And typically what we find is those holes and voids create the color that will actually look too dark in shade. And you can see here this example where we have the actual paint sample compared to how the material looks if we actually include those voids. Let's actually see this with a small video as well on the next slide, just to help explain. Here we can actually see the sample, the same type of sample, those cracks and voids, and we want to be able to measure that. As we take this sample, we put it under the device, we'll see that the instrument where we can actually target, we can see those challenges, and it will actually perform a number of measurements and create an image stack. That image stack will allow us then to be able to create corrections for it. And this is really where X-Rite's technology has advanced in, first of all, being able to create the image stack, then also being able to automate the corrections. These corrections are based on machine learning algorithms where we've assessed how those textures, how those cracks, and how we can remove the different artifacts to be able to come to a visual agreement. Here's another example of this as well. We talked about this carpet, and if any of you have ever tried to match a piece of carpet, especially one of these sort of long piled shag type of carpet, with a spectrophotometer, in the past we'd have recommended use a benchtop spectrophotometer with the largest sphere possible, because that's going to give you the best chance of illuminating the area and try not to lose the light within the fibers of the sample. That has some real problems, because again, often you might then get fibers inside the sphere, which doesn't help. We will still see light loss within these fibers, and also we have what we call these sort of gloss and glint areas. Here you can see an extraction. So as we start to actually look at the image, we can analyze the image, and we can actually take the pixels that are the common pixel areas removing the inconsistencies to be able to achieve a visually acceptable match. Here's Elmo. Elmo is a fluffy type of material. We saw previously these voids where we were losing light, but also it's important to see these even more of these glints and these fibers, because if we have these highlights, especially where we have sort of bright illuminations, that can actually artificially lighten the color. It actually make it sort of even sometimes sort of more lightened, but also make it less chromatic. Here, where we're again extracting, we can actually analyze and pick to the true color. That's really what we call our smart spot technology. But additional to smart spot technology, we also want to be able to think about the flexibility to be able to either measure small samples or samples that will have may have multiple colors within them. There are really two ways we can do this. Either we can deliberately target an area, or we can allow that imaging technology to be able to extract multiple shades. In this one we're just seeing now, this one is actually going to do the targeting. So again, we can use the image and then we can actually place within that image the place of interest of the region of interest for the color measurement. Additionally, as I said, we can also do the multiple color extraction. That multiple color extraction does not have to be solid areas of color. It can also be areas of color that are fine, and therefore we can combine them together. So in this example here, where we have a woven fiber, if we try to measure this with a spot color device, you obviously will get some really weird and odd color readings, because it's always going to be a combination of these fibers. When we actually measure this with the hyperspectral, you can start to actually see where the weave components are extracted, and it allows you to be able to actually get to that true color component of the weave. Another example here, this one, again, another sort of practical thing. I assume many people have had times when they've had samples brought to them that perhaps aren't in a consistent form that they would like. You can see on this wood mixing stick, or a person that's painted it out, we can see that it has issues. It has issues where we can actually start to see through to some of the color that's sort of shining through from underneath. It has some inconsistencies. It has some gloss areas for glints and things. It's slightly misshapen, etc. All of these things causing those variances that if we were to measure in a spot color, it would give us an inconsistency. But here you can see, again, where that measurement area is being performed, you can see that by using that image analysis, it allows us to pick out the consistent pixels. It allows us to be able to create a match to the visual agreement. And proof is in the pudding, as I always like to say. Here are some real life examples that have been measured on the MetaView device, and a paint match has been performed to be able to visualize and see exactly how it works. This was a bath scrubber, and again, as you can see here, if we were performing a measurement on this, that would have measured in the holes, but obviously using the image extraction allows you to be able to get a good match. This one is probably a relatively easy one, because again, here we can zoom into a small area, be able to achieve the color match. Here we see examples, again, picking out colors from an image area to be able to perform measurement. And here, again, those measurements on the various, again, in America, we call it stucco, but in here, we call it obviously facade or textured paint, to be able to remove those variances. The next piece I'd like to talk about is non-contact measurement, because one of the challenges that we have is with traditional devices, you need to actually place the sample directly against the instrument. And unless that paint is absolutely perfectly dry, typically what happens is it sticks to the spectro and therefore is going to potentially damage your spectro, especially if it's a sphere-based instrument where you don't want to have any contamination going inside that sphere. If we can work in a way that has a ability to measure wet samples, this obviously can bring us some advantages as well, because potentially we can actually speed up your quality control process, your matching process, or any type of method that we can correlate between. I was also very pleased a few weeks ago to be invited to go to the Salford University, where we got to actually work with the students. They had a apprentice type style exercise where they had to actually do a color match to this grey sample. At that time, I thought, maybe I should take the MetaView along with me rather than one of our contact spectrophotometers, because again, I expected that they were going to be challenged for time and they needed to be able to measure those samples quickly. And obviously I didn't want to contaminate my my benchtop spectro at that time. What is really important to understand here is though that all or nearly all paints have some type of change process as they're drying or curing. We can see the example here that I've actually created a color standard for both the dry material and the wet material. Here we can actually see that color difference as an example, and it was coming out like 1.7 delta E color difference, obviously mainly being lighter in shade because it's emulsion paint, when it was wet in comparison to the dry, which obviously went darker later on. The important thing when we're thinking about doing this correlation between wet and dry paint is to understand where your plateau of change is. Being a non-contact device, the MetaView is also ideal as well, because we can put a sample in immediately after it's been drawn down, applied, whatever it is, and we can measure then. And we can also set the system up to measure at specific periods of time. And that will allow you to understand and optimize where your color change occurs at what period in time. What we want to be able to see is, can we create a correlation between the wet paint to be able to perform either a correction or be able to do a pass-fail to say that it's going to be the same when it dries. Now, emulsion paints aren't too bad because obviously we can dry those relatively quickly. It's obviously a lot more challenging. I've seen these types of examples when we're using it for things like gel coats or things that need to have like longer curing times. And these give you real distinct advantage if you can actually set up the correlation between the two points, the reference points. But again, all of it is really down to that ability to be able to measure in a non-contact way. Getting to measure in that non-contact way might be somewhat of a challenge, because we need to be able to position your samples in the best place for this. And here you can see just a few examples of how the MetaView has a range of accessories that allow you to be able to either put it on a stand, which allows you to wind it up and down, adjust the height, also to place it into a holder system. So these small spoons and dishes, etc., allow us to be able to fill them with material, place them in here, not have contamination of the device, and to be able to make those measurements. And lastly, again, all of this solution is also supported by what we call our Net Profiler. Net Profiler is a piece of software that also is in combination with calibration or profile tiles, which allows you to be able to check and determine that your device is performing within the specification. And also, if we have multiple devices, especially devices which have aged, because as devices become older, perhaps they become contaminated, perhaps the components start to degrade over time, and we can actually use that profiling technology to bring devices closer together. And really just to wrap up then, in fact, I've gone perhaps slightly quicker than I had thought, but I'm interested to actually start taking some questions in a moment if you do have some questions. As a reminder then, this is a 45.0 device. It provides a spectral image. it provides resolution of that 400 to 700 nanometers. In terms of our spot color measurement, because again, we can force it to choose between different sizes, it will allow you to actually measure between that 2 to 12 millimeters. And the actual working distance for the non-contact, it is quite close, it's 3.1 millimeters, but again, the important thing is that it's obviously not making contact in that surface. Okay, Nikki, I'm not sure if you're there, but I think we're on to the Q&A.
I am here, I'm back. Thank you very much, Matthew. That was really, really fascinating and a very impressive piece of kit. It would certainly have made my professional working life a lot easier back in the day. We were asked to colour match some very weird and wonderful objects, not the least of which was a live horse. So, so we do have some questions coming in. The first of which is from Roger Brown. So hello, Roger. So firstly, based on one of your first slides on the spectrophotometer geometries, would you consider the 045 to be a superior geometry to the D8 for the paint industry?
That's a really, it very much depends on what you want to do, because again, the 045 does take into account the appearance of the sample. So if you want to have the best visual agreement, how someone else is perceiving it, then in theory the 045 is the best. But having said that, if you're wanting to compare a matte paint to an NCS semi-gloss sort of standard, you will have obviously a variation there. And that's when the sphere instrument has an advantage, because again, measuring the spectre included. In fact, I don't know if you can see from my camera here, here's a piece of plastic. So on that piece of plastic, it's going to let me, I shouldn't have my blurry background on, but on that piece of plastic where it has a variation in gloss.
Yes, you can see that.
Yeah, where you can see that variation in gloss between the two sides of it. If I measure that with its specular included, it will see that plastic as being the same color. And that plastic is the same color because it's one same piece of molding. So it's always dependent on what you need. So I would say that a 045 instrument gives you the best understanding of the appearance of the sample, whereas a sphere instrument allows you to compensate and to be able to see the underlying color. Okay,
thank you for that. And Roger again, this one's, just bear with me while I read this one out, please. So in the use of hyperspectral imaging to get a true match to textured colours, is the practical goodness of the match dependent on the viewing distance? So for example, when seen up close, where the texture is visible, the brain will compensate for the shadows and will see the true match. However, when seen at a distance, when the range is too great to see the texture itself, will our brains not interpret the colour as the average, similar to the spots measurements, meaning that the true match now appears too light? Would this be an example of viewing distance metamerism? Brilliant question, Roger.
Yeah, yes. So the answer is yes, and that there is dependency on how close you are. This is very similar to as we see in the automotive industry when you have different flake sizes in your paint, in your metallic paints. And our algorithms have really been based on typical viewing distance. So when we've actually trained the systems, we're actually looking typically when people are using the standard observation of arm's length. Now, as we then move further away from the object, you also have to, I suppose, take into account that you're getting a much larger diffuse illumination. If, for example, we took this outside into a sunny, bright environment, you have less of those shadows occurring because you have a much wider diffuse area. But again, it's really the objective here is to, again, have a match at arm's length, which is the typical sort of viewing conditions of most paint technicians and also most customers.
Okay, thank you. We have another question from Ward Bossoit. I apologise if I've mispronounced your name. Can you use the measured colours with these types of devices in a colour matching system and software?
Absolutely. So all of the, let me just go to the one here. all of these here, these paint samples, these were made from in our color matching system. So either our X-Rite iMatch software or our point of sale color designer software. So yes, and the other thing, it is possible to combine devices. So we can use our spot measurement devices to actually create the paint calibration data, because to be honest, if I'm measuring all my samples on these nice homogeneous paint areas, there is no advantage in using a hyperspectral device because it just sees a solid area. So you can perform and create calibration data. It has to be, in this example, a 045 geometry, but then later on, there's no reason why you can't use the hyperspectral with calibration data that's come from a spot device in a full match prediction or correction.
Okay, thank you very much. There's another couple of questions that have come through on the chat. So the first one is by Maximilian Musseter. Thank you for the interesting presentation. How large is the area of 1 pixel and how many pixels are averaged in the end?
Oh, now you're putting me on the spot to try and remember those ones there. We use a method called pixel binning, because if you actually look at an individual pixel, so from memory, the camera in the MetaView is something like a 5 megabyte resolution, but we actually find that going at a pixel level is not that helpful, because we have what we call crosstalk when you actually look in how the pixels interfere with each other, and we always use a method called binning, so we actually sort of group them together. I can't remember off the top of my head what the resolution is. I believe it is something in the 0.2 nanometer maximum resolution, but again we use the binning, and generally across the 12 millimeter area of view, which is the largest view, after we have done our binning, that actually results in a view area of 330 pixels by 250 pixels. So again, that's like we combine them, not pixels, but how can I call it, bits or bins.
Okay, thank you. The next question is from Zara Bergman. We put translucent coloured coatings onto metal substrates. The substrate gloss often gives inconsistent readings on our spectro. Would this technology be useful for eliminating the substrate effects?
So let me just check this. So we have a metal surface and they're putting a
translucent coloured coating.
No, this would not be of help for that challenge. In fact, a sphere-based instrument with the largest integration sphere possible would actually help to get the most homogeneous measurement. With the one understanding of, is that metal surface a smooth metal or does it have brushing? For example, when you have a brushed steel, in those circumstances, there may be some interest to use a sphere instrument with a hyperspectral, and yeah, that might be a future option.
Okay, Zara's just confirmed that it is a brushed grain texture.
Yeah, okay, so you need to, okay, so it'd be great to talk to Zara on a one-to-one type of thing if you'd like to sort of get in contact and we can explain some further options for that. But yes, you then need a hyperspectral with a sphere instrument to be able to capture the specular included, but then remove the texture of the brushing.
Okay, thank you. And then I think this might be the final one. So if anybody's got any burning questions, get them through now. From a Kimberly Zhang. How is the normal mode different from the smart spot?
Let me find a good slide just to sort of talk towards that one. The normal mode, if I was to measure this sample here, I would just actually choose an area, a size. So I'd actually say that I want to measure a 2 millimeter or a 10 millimeter, and it would still perform then the measurement in there. So we're basically including all of the pixels, but then just masking out the ones around it. in the smart spot type of technology, whenever we've got smart pieces in there, in fact, let me also go back to that other texture one as well. Whenever we have smart switched on, so again, back to here, whenever smart is switched on, it takes, actually it's not the best one. Let's go for, yeah, whenever we have smart switched on, it automatically picks the pixels which it believes are the best ones to use. And again, that's based also then on that algorithm to do the correction based on the visual assessment.
Okay, thank you very much. Well, I don't think there are any further questions. So if I could just take control back, if that's okay.
Sure.
And move on to our final slide. So thank you very much, Matthew. That was really very interesting. If anybody has any questions that haven't been covered or would like to speak to Matthew directly, please get in touch and we can make that happen for you. So it just remains with me. So we'll be on a break next week, obviously, because next week is Surfex. So all of the OCCA team will be at Surfex. So the next webinar in our series is on the 15th of June, and that will be given by Synthema. And then we have another, sorry, I'm just trying to go between screens, another 2, 3, 4, another 5 left of this series. So the webinars are, we have 65 webinars in total to date. So we're now on series 7 and they are offered free to members and non-members alike. And once you've registered, the links to the session recording and the slides offered to all attendees and OCCA members. Since its inception, we've had over 60,000 registrations and 4,000 attendances. So I'd just like to thank everybody for your attention today. And if we don't see you at Surfex, we'll see you in 2 weeks.
Yeah, and I'll just say as well, I'm going to be at Surfex on the 8th of June. So if anyone wants to pop by, I'll be more than happy to talk with you. And we'll also obviously have all the X-Rite equipment there, which we can play with at the same time.
Thank you, Matthew. And thank you, everybody. Have a good afternoon.
Thank you. Bye-bye.
Bye.